can't see, so like feel free to move over as much as possible because that's kind of small. But I think we all brought the reviews that I printed out, hopefully, most of us, so that's good. Oh, jeez. And it's sideways. Cool. Is this okay to see from way over there, or no? Also, this is like being streamed on YouTube, so maybe you could go on that and you'll see it better. I don't know. Okay. So I guess we'll just start, and hi. What is the video called? Do you guys know?
It should be the name of the session. It's on the Start YouTube page.
Okay, well, I guess we'll start. Sorry, you just try to move over, I guess. But so for number 1, what do we think? Oh, this is the answers. Cool. So for number 1, does anyone know what it might be? The question is, how would you describe the sign values of delta H, delta S, and delta G for the freezing of liquid water below 0 degrees Celsius? It's from chapter 18. Okay, he says delta H would be negative. Why would that be? Okay, so the negative means it lets out heat? Yes. Nice. He said the freezing of water is exothermic, so that's why delta H would be negative. What about delta S? Okay, why would that be? Okay, so delta S of the reaction is final minus initial, and it's going to end up having, so like in liquid it's more like disordered, and then when you go into solid it's just like blocks a little bit. That's how they usually describe entropy, so it has less disorder when you freeze it. And then delta G, does anyone? Yeah, exactly. So we all know that water freezes below 0, so negative delta G means it's spontaneous. Cool. So for number 2, the melting of snow above 0 degrees Celsius results in the increase of entropy in the universe. True or false? True or false? Dang, I'm hearing both. So is there like a law that someone would know that could help us? What does that say? Yeah, but what does it mean? Okay. Well, it deals with entropy, so that's good. Well, from the slides, it says that for any spontaneous process, the entropy of the universe increases. So it doesn't necessarily have to do with the entropy of the reaction, just the universe. And we know that snow melts above 0 degrees Celsius, so it's spontaneous. So we know that the entropy of the universe increases. So it's going to be... Not always. Sometimes the entropy of a system decreases, like in the first one. But if it's spontaneous, the entropy of the universe increases, according to the second law. So, number 3. Also, if I ever, this is like out of view or something, feel free to yell at me. Number 3, the spontaneity of a reaction is not necessarily related to the speed of a reaction. True or false? It's true, right? Can someone explain that, kind of? All right. It's just not, I guess that's just a rule. So I don't know what someone was supposed to say. But so more on thermodynamics. What signs for delta H and delta S will make a reaction always spontaneous? Negative for both of them, or? And positive delta S. Okay, why would that be? Okay. Are you talking about like the table that you memorized? Okay. Well, there's the table and there's also like equals delta H minus T delta S. Hopefully familiar formula. So if it's spontaneous, like we said earlier, we want negative delta G. So if this is negative and this is positive, the negative sign is like going to turn that into a negative. So it's negative, and then you add more negative, and yep.
It could also be, delta G can also be negative, like if delta H is positive too, since it's being moved by the temperature. Delta S is being moved by the temperature.
Mm-hmm. Yeah, it can. These can be anything, and it still be negative. It just depends which one is bigger and which one is more negative. But the question is asking which signs will make it always spontaneous. So otherwise, if they're not negative and positive, it'll depend on the value of T, but here it does not.
So what is the full definition of
Spontaneous, the definition? Does anyone know like the definition of spontaneous? Well, it just happens, like she said, without you like forcing it to happen, I guess. Ball rolling down a hill, something like that. You don't have to drive it forward. It just happens on its own. Mm-hmm. And it might take a long time. I think we have another question on it later. That might clear things up a little bit. So, for number 5, which compound is more soluble in an acidic solution than a neutral solution? Does anyone have an idea of where to start at least? Is it D? Okay. We'll mark that for now. Why would it be D? Okay, that's part of it. So later in the review, I put it in a weird spot, but there's like a list, and it says, it has a mnemonic on it. Where that is, I'm not sure, but it's definitely in there probably. But it's CSI and NBC for memorizing your strong acids and bases. Hopefully we all know them by now. Does anyone want to list off the strong acids? HCl, okay. HNO3, okay. HBr. And one more. HClO. sometimes 4 and 3. This one's not as important as the rest. You don't see it as much, but it's on there. So these are your strong acids, and does anyone remember the strong bases? I don't have a periodic table, but like how to memorize them? Yeah. Yeah. So if you look at it like that, it like makes like a B a little bit. And these are the first half of the strong bases. But so knowing these will help us with this problem. So whoever said D, would you care to explain why it would be D? Okay. So how is this different than these three? How is D different, I wonder? It has a fluorine, okay. So on all of these, there's Cl, Br, and I, and those are part of the strong acids over here when they dissociate. And strong acids, we know, dissociate completely, right? So they are not going to affect the solution in any way. But we need to solve BaF2. It's going to make BaF2 is going to be BA2 plus 2F minus. So these two are going to dissociate into these in a solution. And in an acidic solution, that F minus is going to come together with the extra hydrogens in the solution, and it's going to take away some of these. And then the reaction is going to proceed more to the right than in a neutral solution. Does that make sense? So if you did it with AgI, for instance, you would have AgI goes to Ag plus and I minus. And in here, unlike the fluorine, the iodine is not going to come together with any hydrogens. So it's not going to have an effect on how much this dissolves. Cool. So we'll go to number 6. So this is kind of the same thing. Describe whether the following compounds, when dissolved, will produce an acidic, basic, or neutral solution. What about NaNO3? Neutral, okay. Because Na is part of a strong base, and NO3 is part of a strong acid, so they're not going to come together with any hydroniums or hydroxides and change the pH. What about KBr? Neutral as well. All right. And then C. Basic, I'm hearing. So when this dissociates, it's going to be K and CH3O minus. So acid, or this is going to be a base, and it's not a strong base, so it's actually, well, yeah, it's a weak base, so it's going to take some of those hydrogens, and it's going to make this basic. But the other ones were part of strong acid, so they would not do that. So on to number 7. Which manipulations will shift the reaction towards the products? And then I took away, on the later version, I took away this and this because we didn't really talk about it in class. They're still like true, but so from like 1, 4, and 5, what's going to make the reaction go to the right? Okay, so there's that. Cool. And removing H2O as well, or no? Yes, okay. So all of them, right? This is,
Wouldn't one be wrong because H2 is an inert gas, so that wouldn't do anything?
an inert gas. Well, it's part of the reaction, so it's doing something. Okay, like he said, if it was added to the reaction, that's already doing something, but it's not part of it, then it wouldn't affect. But it would do something with the pressure, I think. But in here, it is part of the reaction, so it is going to affect it. So yeah, if you add something to this side, it's going to proceed to the right, and all these are doing that. And then this one's taking away from this side, so it's going to proceed to the right as well. This is Le Chatelier's principle. I don't really know how to say it. Cool. Does that make sense to everyone? Off to 8. So which one of these processes has a positive delta S? Kind of back to what we were doing before. Two is going to have a positive, and that's it? Or okay, so we'll go one by one. This one has 7 moles on this side, and this one only has 2, so that's decreasing entropy. And then also it has gas, and it goes to solid, and there's no gas on this side, so that's more decreasing entropy, so this one's definitely going to be negative. This one has more moles on the right side, and also it goes from solid and gas to just gas, so it's going to be positive entropy. And then this one is going from gas and gas to solid and liquid, so the entropy is going to decrease in those. So only 2. All right. So number 9. Question. Both of them affect the entropy, so you just have to take both in consideration. But for both of these, both of them are making it less entropic, so it didn't matter. But if not, there would be like a tiebreaker or something. Like if it was all gas, then you would go to moles, or if the moles were the same, then you would count gas. Yep. So number 9. We have a reaction, and we're trying to find the delta S, and we also have a table with all the compounds in it. So what should we do? Okay, so we have a formula. S of the reaction equals products minus reactants. And then it's the delta S of them. It's like the sum. So that's the formula. So we're just going to add these together and see what we get. So P4O10 is going to be negative 2034. And then H2O is 321, but it's going to be times 6 because there's 6 moles. And then this we're going to put over here at 1374. And it's going to be times 4. Times 4. Do we have calculators? So what should these numbers be? Did someone want to say? Okay. 3960. Negative 5496. Okay. Which gives us B. So this turns into a plus, as we know. And it gives you this. Cool. And then there's a lot of questions like this that you'll see. You'll see it with like delta H instead, or also delta G, and you do them all the same, pretty much. Okay. Any questions on that? Pretty straightforward. This one is a lot like the last one, so we'll just skip it. You can do it on your own. The answer is B, though, because we have a lot of questions. So we can just go to number 11. So we're supposed to be determining the temperature at which whatever this is boils in the reaction below. And we have the equation for it, and the delta S and delta H. So what should we do with that? Did someone say D, I think? Okay. Well, that's the answer, I think. But so maybe we could use this equation again. H minus T delta S. So we have a liquid going into a gas, which is boiling. So that's what the question's asking for. And we're trying to figure out when this happens, what temperature. So we want to figure out where delta G is negative, which is spontaneous, like we were saying before. So we'll set this to 0, because that's where it switches over from positive to negative. And then we'll just plug in the delta H and delta S. Well, we'll just be solving for temperature, but yeah. So it's 38 times 10 to the third minus T, and then 113, right? And then the reason it's 0 is because we're trying to figure out when it boils. So we have the equation going from liquid to gas, which is boiling, and we just want to know when it will be spontaneous, at what temperature it will be spontaneous, and 0 is where it turns from positive to negative, which is non-spontaneous to spontaneous. Yep, another question? Yeah, we're going to be adding them, so we do want to convert them. That's really a good thing to think about. A lot of times, every time I've seen it, they give you enthalpy in kilojoules, and then they give you entropy in joules, and that messes a lot of people up because you have to convert them. So that's why I put the 10 to the third over here. So that, I should have wrote the units out, but this is also in joules, and now this is in joules as well. So then we solve it, negative 38 times 10 to the third, negative T times 113. And then we just divide both by negative 113, and that'll give us our temperature in Kelvin, which ends up being 340. So it's D. Is there any questions on that? Cool. So for number 12, we want to know the Gibbs free energy change for the dissociation of hydrofluoric acid and H2O at 298 Kelvin, and we're given the Ka. So how would we go about solving this? The same reaction we just used? delta G equals negative RT ln K. So yeah, a lot of times when you see delta G, you think of this equation, but you forget about this one a lot of times. And since we're given the Ka, we know that we use this one instead. And we don't have delta H or delta S for the equation, so. Okay. And we'll just plug it in like the last one. So delta G equals negative, what is R? Does anyone know? Okay, 8.314, and it's joules per mole Kelvin. And we will come back to that in a second. Ln K, and K we're just going to use this. So then after we multiply those out and take the natural log, we are going to get C, I think. I did forget the temperature, but it's 298, so. Is there a question?
It is 8.314, but when do we use 0.08206?
Yeah, so that is a really good question. And let's see. So there's two gas constants we use throughout the semester in different kinds of problems. There's 8.314 joules per mole times Kelvin, and there's also 0.08, what is it, 205? Oh, 0.6, it's right? Is that what you're saying? Okay. It's not a huge difference, but, and this one is liters times atmosphere per Kelvin mole. So when to use them can sometimes get confusing, but if you just look at your units, you'll kind of figure it out. Because this one is dealing with entropy, or not Gibbs free energy, that's what I meant. And we have joules in this form of the gas constant. So we know that we'd be using this one for this problem. And this gas constant is for problems with like pressure and stuff. That's why it has units of atmosphere instead.
For the ln K, do you just plug in Ka for the K?
Yeah. Sometimes you see the equation with ln Q. That's when it's like not at equilibrium or something. But yeah, so I just plugged in 7.2 times whatever, and that gave me the answer. Is there any questions on that? Maybe, but we haven't really seen that so far. So I don't. Yeah, so if they gave you KB, but it just depends on what the equation is as well, because if it was a base dissociating, then you would use KB. So. In this kind of question, hopefully not, but then you would have to convert it, and that would be a pain.
So the natural ln K and the natural log. Oh, great. That we apply the equilibrium constants for ln K.
We use the dissociation constant in for K. Is that what you're asking?
Yes.
Yeah. Yeah, we just plug that in. Oh, okay. Well, we already have T in the equation. I wrote it kind of sloppy and I forgot it, but T is over here, and then you have K over there, so beware of that. So go to 13. This is a kind of question you see a lot on the ACS, so we didn't do it in class, but I remember it from when I was in Chem 2, so I put it on here anyway. And we did do it, it just wasn't on exam. So we're determining the rate law for the reaction between nitrogen oxide and chlorine to form nitrosyl chloride. That's not super important. So any ideas as to how to approach this?
We're going to need to find
Okay, we're going to need to find the reaction orders, he said. So how do we do that? Do you have a question? Oh, okay. Okay. You keep going, sorry.
We find the concentration in which the event in which the concentration doubles and the concentration of another substance stays the same.
Okay. So he said we're going to compare when one of them doubles and one of them stays the same and see what happens to the reaction rate. So these are going to be experimental results from like in a lab or something. And what they're doing is like changing the concentrations of each. And we want to see how the reaction rate changes when you only change one of the concentrations so that we can know how to write the rate law for it. So remember the rate is going to equal K times A times B. So we want to write that for this equation. So we're going to see when one of them is the same and the other changes. So between the first and the second one, this stays the same. So it's times 1. And then this one changes the concentration of NO. So, and we're going to see what happens to the reaction rate, which I think it gets multiplied by 4. So due to that, we know it's second order, because if it's doubled and then we put it to the second order, it's times 4, right? So we know the rate is going to be K times NO squared, and that's all we have so far. So then for chlorine, we want to see where NO stays the same and it changes. So between these, it's times 1. So we know that we could use this to compare the rate. So we have times 2 here. And then this one is also going to be times 2. Yeah, so it's a 1-to-1. So we know that we could do Cl to the first power, and then that's going to give us E. Okay, and then based off of that, we're going to do number 14, which is just a continuation. Try to zoom out a little bit. So we want to use the results from that problem to find the rate constant for the reaction. So how do we do that? What was that? Yeah, we'll just use algebra. We'll plug in one of the trials from up here and into this equation, and then we'll figure out what K is. So we'll just use the first one because they're usually the smallest, so the easiest to work with. So we have rate equals K NO2 times Cl to the first power. Oh, this is squared. So for the first one, the reaction rate is 0.117 equals K. And then this is 0.1 squared. It's the opposite. I mean, they're both 0.1, so I might have pointed to the wrong one. And Cl is also 0.1, and that's to the first power. So 0.117 equals K times 0.1 to the third. And which answer does that give? Cool, so that's B. Does that make sense to everyone? That was kind of long, but cool. So, some acids and bases. For number 15, by the Bronsted-Lowry definition of acids and bases are proton acceptors, someone says, and then any other ideas? It's over there. Okay. Anything else for this one? You think it's C? Okay. So that's all here. So I guess it's between those two. We could rule out A because proton donors are definitely acids. We just think of like HCl or something. So we know it's not that because we're trying to find bases. Proton acceptors kind of makes sense because that's what bases do. And also make OH groups make sense as well because when you think of like NaOH, that's a base. So, and then for D, form hydrogen bonds. That doesn't really make sense for acids and bases. So by the Bronsted-Lowry one, it's actually our proton acceptors. It's B. Make OH groups is by the Arrhenius definition, I think. So, but they're both definitions of bases, just using different terminologies. So. And then for 16, the stronger the acid, which one would it be? B? Yeah, the weaker its conjugate base. So we could use HCl again to think about it. HCl is like the strongest acid there is, and then if you do Cl, it's so weak that you don't even consider it as a base because it's not going to associate with these anymore. So for number 17, this is from before, but which of these have a dipole moment of 0? Okay, CO2, someone says. We'll just go through them. So for these kind of questions, you want to draw out the structures so that you can visualize it better. So we have C, O, and there's electrons around them, but that's not super important right now. We know that oxygen is way more electronegative than carbon, so it's going to be polar. So it's definitely not A. B is C, H3, COH. That's probably wrong, but we know there's an oxygen and also carbons, so it is going to be polar towards the oxygen because it's electronegative. CO2, and these might be double bonds, I think. Oxygen and carbon are still in here, so there is a dipole moment between two atoms, but here they're going to cancel each other out. So the overall dipole moment is going to be 0. And then CH3OH is just like this one without another carbon. So these will be wrong, and the answer is going to be C. So then out of these, which would have the highest boiling point is another question that the ACS does a lot. B? Highest molar mass, okay. Yeah, so it has hydrogen bonds and the highest molar mass. So out of A and C, C is going to be probably the lowest because it doesn't have a lot of intermolecular forces going on. And then A does have a dipole moment, but that's it. And then, so it's between B and D because they have hydrogen bonds and they're polar, so they're going to have dipole interactions. So between B and D, you go by molar mass because then it goes down to the dispersion forces between the two. So the answer is B to the boiling point question. Here's number 18. He just did this in class on Friday. I made this before that, so yeah. It's going to be B. Does anyone not know why it would be B? Yeah, so between these two, the conjugate base or acid is going to be H2O. The rest of these, the only difference between them is one H plus atom, and between this, it's like 2 steps. So that's why it's not the same as the rest. Oh, here's that thing I was talking about earlier that I couldn't find. So for number 19, if the concentration of OH is whatever, then what is the concentration of H? How do we do that? Okay. 1 times 10 to the 14. What is that? Equals kW. Okay. So in a regular solution of water, or any solution, the amount of hydronium and hydroxide concentrations added together are going to equal that number. So we're just going to do times 10 to the 14 equals 0.00532 times H plus, and then that'll give us one of these. I don't know which one. C? Cool. And then with all of these, there's 2 ways to do them, like he was saying in class. This is much easier in this case, but you could also convert it to POH, which is taking the negative log, and then you would do pH plus POH equals 14, and then so you would find POH from that, and then you would find pH, and then convert it just to H. It would give you the same answer, but it's a lot harder. Okay, for number 20, there's no answers, but if you dissolve NaCl in a solution with a pH of 3.8, what will be the new pH? It would be the same. Yeah, it's not going to change because, like we were saying earlier, Na is part of a strong base, so it's not going to do anything, and then Cl minus is part of a strong acid, so it's also not going to do anything. Yeah. Whoops. So we go to 21. So kind of like the last one, if you dissolve NaF in a solution, how would the pH change? It's not the same as the last one. It's a little bit different. So we'll think of this dissolving, and we'll get Na plus like the last one, and it didn't do anything because it's part of a strong base. But then when we get to fluorine ions, I'm not going to write out the equation or anything, but we know that fluorine is a weak base, or a weak acid, not strong, part of a strong acid. So it's going to do what to the solution? Make it more acidic or basic? Basic, yeah. Because it's going to associate with some of those hydrogen ions in the solution. Does that make sense to everyone? Cool. So to number 22. What is the pH of a 0.01 molar solution of acetic acid? And we're given the Ka. So how do we approach this? All right. Well, it's chapter 16, and that was a lot of ice tables and stuff, so maybe we could start there. Or just writing out the equation is always a good idea as well. So we have acid plus H2O and water, and that's liquid. Right, hopefully that looks familiar, and these are both. And then we'll do our ice table. So what would we plug in for our first column here? 0.01, because that's our initial concentration of acid. I wrote HA. That's usually what you do because it shows the hydrogen with whatever the acid is. Sometimes it's a little more confusing when you try to write out acetic acid, like we don't even know what that is. So, and then over here is the A showing the acid without its hydrogen. So now it's a base, the conjugate base. So for the initial concentration of H2O, what's that? Yeah, we disregard it because it's a pure liquid. And for these two, they're both 0. All right. For the change, what would we put?
Minus x on the left side.
Minus x, okay. Plus x, I heard. Cool, so we don't know how much it's going to change. So we're just going to put x. And then at equilibrium, what are the concentrations going to be? 0.01 minus x, and then 0.01, oh, this is just x and x, right? So from here, what do we do? So I'll just write it here. So we have Ka equals x squared over 0.01 minus x. That's how you write those dissociation equations. Yeah, we plug in Ka because that's what we're given. So we'll do 1.8 times 10 to the negative 5 equals x squared over 0.01 minus x. What should we do right now? Yeah, take out the x, because Ka is very small, so we know that we could disregard this to make the math easier. It'll still give you the same answer, but why did we get rid of x? It's because the Ka is very small, and we know that the concentration of x is going to be very small. So if we're taking away the concentration from 0.01, it's not going to make a big difference. All right, so we're going to multiply both sides by 0.01. And then we get x squared, equals, I don't know what this number is. .8. Oh, 1.8? That's a 1. 1.8 times 10 to the negative 6 times 10 to the negative 6. Oh, I guess it's 7. Cool. And then we'll just take the square root of both sides. So we'll get x equals times 10 to the what? Negative 3. Okay. So we have x. 1.3 right here? Okay. All right, 4.2 times 10 to the negative 4. Cool. So now that we know x, what do we do with that? Yeah, negative log. Because it's the H3O concentration, which is the same thing as just H. So we're finding the pH, which is the negative log of H concentration. So that's what that is. So then we'll plug that in, and I think that gives us D, right? Cool. Nice. Any questions on that one?
Wait, find pH in the negative log of the hydrogen concentration.
What was that?
What role does hydronium play in logging pH, in finding the pH again? What role does it play?
Okay, so a P in front of something just always means negative log. So there's POH is negative log of the OH concentration. So here we have pH, which is the negative log of the hydronium concentration. So the whole time we are solving for X, which is the hydronium concentration, because you can't really have hydrogens floating around. They always associate to a water. So it's the same thing, H plus and H3O. So once we found that, we took the negative log of it, and that gave us the pH.
Okay, so it would be the same if we find the negative log of the hydrogen concentration with the hydronium concentration.
Yeah, they're the same thing, I believe. Cool. Is that it for that problem? Nice. 23. So a solution has roughly equal amounts of a weak acid and its conjugate base. The pH of the solution is 7.3. So what is the most likely pH of the solution after you add a little bit of acid? A, someone said? All right. Why would that be? Yeah, so it made the pH a little bit lower, but not a lot, because the solution has roughly equal amounts of a weak acid and its conjugate base, and we know that that makes a buffer. So the solution is going to be resistant to pH change. So that's why like 2.6 would be wrong, because that would make it way more acidic. In a buffer solution, it wouldn't change that much. And then 7.4 and 12 are both higher than 7.3, and we added an acid, so it's not going to go up. It's just going to go down. So that's why that's right. So for 24, in a buffer solution, if the concentrations of acid and conjugate base are equal, what is the relationship between pH and pKa? C. They're equal. Okay. How do you know that? Is that just something you remembered, or? Okay, that is one way to do it. We also know the Henderson-Hasselbalch equation, which is pH equals pKa.
Plus the log of the base divided by concentration of the acid.
Okay. There's like two forms, so I didn't know which one you guys learned. So if concentrations of acid and conjugate base are equal, then we're finding what pH and pKa are. So we just pretend these are both like 1 or something. So it's 1 over 1, and then the log of 1 is 0, which is just like a math rule. So cross this out, and pH equals pKa. So for 25, we're finding the pH of a buffer solution. So what are we going to use? The same equation from last one, yeah. So we have pH equals pKa plus log of acid, or base over acid. So pH equals, we have Ka, and we have to remember to do negative log to get pKa, so what is that? 9.31 plus log of, which one of these is the acid? HCN, yeah. And this is its conjugate base because it's going to go to K and Cn minus, it's K plus, and then like we said before, K is part of a strong base, so it's not going to do anything. So we just have this base here. So the base is 0.17, and then the acid is going to be 0.25. And when we work that math out, I don't know what we get, but 9.14. 9.14. Cool. Does that make sense to everyone? All right. So we'll go to 26. The answers are on the back of the page, so we'll just have to come up with it on our own. If the rate of formation of ammonia is 0.345 molar per second, what is the rate of disappearance of N2? And here we have the equation. So we know that this is 0.345, and we're making two of them. So if we're looking at this, what would it be? It would be half. Yeah, so 0.345 over 2, because the coefficient here is 1, and the coefficient here is 2, so it's going to be 1/2. So it's going to, and the answer's back here. It's probably this one, if you calculate it. Does that make sense? Go back to how to solve it. Okay, yeah. So we're forming NH3 at this given rate. So to make 2 NH3, you only need 1 NH2, because the coefficients, the stoichiometry of it. So we're making this fast, but we only need to use N2 half as fast. So it's going to be disappearing at half the rate that this is appearing. Hopefully that makes sense a little bit more. 27. The first order reaction, C to D, has a K of 9 per second. If the initial concentration of C is 0.6, how long will it take for C to be 0.1 molar? So this is pretty different than what we've been doing. Any ideas for this? Maybe there's an equation that we would know. It's related to the half-life equation. Usually if you need to use that, it'll say like half-life somewhere. But yeah, we're going to use the integrated rate law, which you don't need to memorize, luckily, so that's good. So I'll just give it to you, which is, we're going to write it up here because there's more room. So it's A T equals A. What? Oh, can't see it. Cool, thanks. Equals A initial times e to the negative kt. Does this look familiar, hopefully? So what should we plug in for AT? Like, it could be C here. A is just whatever. So we're looking for this, right? So 0.1. Because T is like after time has passed. That's what the T means. So then we go, and this is 0 is initial. So the initial concentration is 0.6. And then times e to the negative k we're given as 9. And we're looking for T, so we'll just leave that as T. instead of the ln's. Oh, okay. Well, yeah, there's like different forms of it, but we're going to eventually do the ln. Maybe you saw like, because the ln gets rid of the e, so sorry if that's confusing, but we'll fix it in a second. We're going to divide 1.6, or 0.6 from both sides. That's going to give us something. .16, hopefully. 167, is that? Equals e to the negative 9 times t. So here we're going to take the ln of both sides to get rid of the e. So we'll get ln of 0.167 equals negative 9t. So why the equation might look weird at the beginning is sometimes they take the ln of both sides at first, like just in the equation, so it looks different, but it's the same thing. And then after we do this math and solve for t, we end up getting c. Is there any questions on that? Nice. So we'll move to 28. So we have a solution containing 99.5 grams of sucrose, and we're given this, and 300 milliliters of water, and we're given the vapor pressure of pure water, but we're trying to find the vapor pressure of the solution. So where do we start for this one? Do we know the equation for vapor pressure of a solution? PV equals nRT. Probably capital T maybe. That doesn't seem right because we don't have volume, I think maybe. I don't know. That's not the exact equation we're looking for. So it's going to be like Raoult's law. So P solution is going to be equal to the mole fraction of water times the pressure of H2O. So we have to find the mole fraction of water first. So we have 300 milliliters of H2O, and that's going to be how many moles? Did anyone figure it out? It's like all the conversions. And that's going to give us 16.65 moles of H2O. And we do the same thing with sucrose because we're finding the mole fraction. So 99.5 grams. And I already found out the molar mass is 342.3 grams in 1 mole. So then we get 0.2907 moles of sucrose. So mole fraction is going to be moles of this over total moles. So 16.65 over 16.65 plus moles of sucrose, which is 0.2907. That's going to give us 0.9828. And that's the mole fraction of water in the solution.
Wait, did you convert milliliters
I did not convert milliliters to liters because we're given the density of water, which is just 1 milliliter per gram. So 1 milliliter per gram is what I use, but that's a good idea. So we have the mole fraction of water, and according to the law we have, we're just going to multiply that by the pressure of water in a pure solution, and that's going to give us the answer.
Is it 0.982 liters? As the mole fraction?
I wrote it kind of sloppy, 0.9828. Is that what you meant? Yeah, sorry about that. So then we're going to multiply that by, oh, we're adding? I think it's multiplying. Where is that? Oh, is that a, does it look like a plus? I meant it's a dot. Sorry. And then we're given the pressure of pure water times 23.8, and that equals 23.4, and that's going to be our answer. And this is just from the slide that he posted. Is there any questions on that? Does it make sense? Nice. Does anyone want to give us the intermolecular forces ranked in order of strength? Hydrogen bonding. Okay. Ion dipole. So these are in decreasing strength or increasing strength? Decreasing, all right. Where does ion dipole fit in this? It's the strongest? This arrow is kind of confusing. I'm just going to get rid of the arrow because I don't know whether it's supposed to go up or down. But this is the strongest to least strong. So I guess strength goes up. Is that wrong too? Yeah. Well, strength is the strongest up here and the weakest down here. So the arrow is not the best. So off to number 30. Which has a higher boiling point? I know we already did one with boiling point, but it's on the ACS a lot. So out of these two, they both have the same formula. So we have to think of something else. The second one, why would that be? Hydrogen bonding, yeah. So that's like the second strongest one. Off to 31. Well, back to the last one. We know that if it's a hydrogen attached to anything very electronegative, it's going to do hydrogen bonding. So if it's like an N or an O, or maybe like a fluorine or something. So that's how we could recognize that this has hydrogen bonding and this doesn't. Because here it's the oxygen's just attached to 2 carbons. So for 31, what do we think? It's B. Okay. Well, it's which of the following statements about catalysts is false? They do not appear in the balanced equation. Is that true or false? Or that's true. So I'm going to cross that one out. They reduce the activation energy for a reaction. That is true, right? Because we've all seen the things like that. This is without the catalyst, and this is the catalyst. So D, catalysts do not alter the mechanism of the reaction and never appear in the rate law. Okay, so we're confused about that one. We'll just skip it. And for E, since catalysts are recycled, even a small amount of catalyst can accelerate a reaction. That one is true. Okay. Oh, I skipped C, which is biological catalysts or enzymes.
That's true.
That is true. Okay. So we got rid of C, we got rid of B. So D was kind of confusing, but we eliminated the other ones. It does alter the mechanism. Or wait, it's false? Yeah, it does alter the mechanism. That's why it changes the activation energy. So this is going to be the one that's false. And this was like from the ACS review. So. All right, last one, I think. This is another rate law question. And you don't know the formula because you don't have to memorize them. So I will just leave that for someone to do at home because we already did one like it. And now we can just move on to any questions you guys had because I said to bring questions. Hopefully you did. Do you have one?
Yeah, do you know what formulas they will give us besides the rate law?
What formulas they will give us besides the rate law? I personally do not know, but in class he was talking about it, right? Does anyone else? Oh, someone has it. Okay. Yeah, we can put it up. Okay. Sure.
Why doesn't have the zero order rate law, but he said all those things.
Okay, here's a lot of stuff. Oh, geez. All right, well, you can't really see it very well, but there's a lot of them, so. So we could see, like, most of the equation we used today were definitely given. Actually, everyone we used today were given, so that's good, but you can't really see, sorry. Yeah. I brought like 3 more questions in case no one brought their own, which it looks like no one brought their own for some reason, so. With Henry's law? I don't think so. Sorry. Is it on there? I'm not sure. That was a long time ago. So no one has questions, I guess? Sure. You could just, thank you.
What's the number given by the facilitator for this?
The number?
It said bubble facilitator.
1.
1?
1. If anyone really wants to bubble it in. Dang. Well, I guess a lot of people are leaving, so now there's more room over here a little bit. If people want to move, but so these questions I just got from the actual ACS thing, so they're probably a lot like what you'll see, but there's only 3 of them. So for number 1, zoom in a little bit. All of these are potential Lewis bases except one of them. Which one do we think it would be? Yeah, for number 1. CH4. Okay. Why do you think that would be? Because it can't accept any? All right. So for these problems, a good idea is always to write the Lewis structures out. So we'll do that here. NH3. We'll do NH. So if it's a Lewis base, it can accept a hydrogen and donate electrons. So here we see that there's 2 electrons to donate and another hydrogen can fit on. So it could definitely be a Lewis base. So we'll get rid of that. H2O, we know looks like this. And we know that water is amphoteric, so it could be an acid or a base. And then we also have these electrons that can accept hydrogens. So we know that that's wrong. CH4. Carbon already has 4 hydrogens on it, and then there's no lone pairs on the outside for it to accept any more. So it can't really act as a base like these 2 definitely can. So that's why that's the right answer. And then Cn minus is definitely going to have lone pairs, and it's also negative. And usually things that are negatively charged are more basic, is a good thing to remember. So for number 2, which is a proper description of chemical equilibrium? We have the frequencies of reactant and of product collisions are identical. Does that sound right? No? Okay. The concentrations of products and reactants are identical at equilibrium?
Yeah.
Okay, some people are saying yes. We will come back to it. The velocities of product and reactant molecules are identical. No. The reactant molecules are forming products as fast as product molecules are reacting to form reactants.
Yeah.
That sounds right too, okay. For E, the number of moles of reactants and products are equal. Okay, no. So we'll definitely cross that one out. So it's between B and D. Are the concentrations of products and reactants identical at equilibrium? No.
Always.
Yeah, not always. That's like a big thing
So it's D.
to make sure you know. Yeah, D. So reactant molecules are forming products as fast as product molecules are reacting to form reactants. So it's going back and forth at the same rate, but what's on this side might be like, 1 and 3. Like they could be different. They're just going back and forth at the same time in the same rate. So number 3. When equilibrium has been reached in the reaction, whatever, and then it's just saying which one is true. So adding AE will increase the concentration of CE, but not AD. Maybe true, maybe not. False, okay. So we'll cross that out. And I know it's confusing with all these kind of abstract things, but that's what the ACS does. It's not a lot of math, it's just weird stuff like this. So adding CD will increase the concentration of both AE and AD. No? Heating will increase the concentration of both AE and CE. Yeah, so it has X and kilojoules, which is energy, so you could think of it as heat. So is this going to be exo or endothermic? Exo. Cool, because you're treating heat like a product. So I think we said this one was wrong. Escape of some AD by volatilization will increase the concentration of CE. Getting yes and no's, so we'll just mark it. Doubling the pressure will increase the concentration of CE. Maybe? Getting absolutely no answers on that one, so we'll just leave it. Okay, so between D and E, escape of some AD by volatilization. That's like a weird word. I think it just means boiling, right? So we're saying AD kind of like escapes somehow. So AD is lowering. We'll increase the concentration of CE. So if AD goes away, which way will the reaction go? To the right. So, and CE is on the right, so this concentration is going to go up, as will AD and as will heat. So it's going to be D. Doubling the pressure might be true, but there's no way for us to know if it's true because we don't have anything with moles or gas or whatever, so it's just kind of irrelevant, I guess, here. So we will cross that out. Nice. And that actually is all the questions I have because I really thought people would bring some. So, or if there's any questions on anything we've done so far, I would be happy to try to explain it again, or we could do it more.
Can you explain
Bi intermolecular, what?
elementary steps?
Elementary steps. Does anyone remember that stuff? No? I do not remember doing that in class. It was on one of the slides? Oh boy, I don't have the slides. If we want, I can look them up, but it would take a long time. So sorry that I don't know that well. But good luck on the exam if you're leaving now. Get a good night's sleep and whatnot.